In the search for extraterrestrial life, scientists use a variety of methods that combine advanced technology and eternal curiosity. One major approach is to study exoplanets, planets orbiting stars beyond our Sun. Using instruments such as the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, scientists identify potential exoplanets by observing the waning of a star's light as a planet passes in front of it. Once exoplanets are discovered, they are analyzed for their suitability for life. These include calculating a planet's distance from the star to determine if it is in a habitable zone where conditions may be suitable for the existence of liquid water, a key ingredient for life as we know it. In addition, powerful observatories, such as the soon-to-be-launched James Webb Space Telescope, will probe the atmospheres of these distant worlds in search of biosignatures, chemical markers such as oxygen, methane, or water vapor that may indicate the presence of life. Another intriguing method involves studying extremophiles here on Earth. Extremophiles are organisms that thrive in extreme environments, such as the intense heat of hydrothermal vents at the bottom of the ocean, the acidic environment of sulfuric hot springs, and the cold radiation regions of Antarctica. Understanding how life can survive in such harsh conditions allows scientists to understand how possible it is for life to exist in similar conditions in other parts of the solar system and beyond. In our solar system, missions such as the Mars rovers, including the latest Mars rover Perseverance, are equipped with sophisticated instruments designed to detect signs of past or present life on the red planet. Similarly, missions to icy satellites such as Europa, which have oceans beneath the surface of their icy crust, are searching for biological evidence of life. In addition, radio telescopes participating in the Search for Extraterrestrial Intelligence (SETI) program are listening for signals from advanced extraterrestrials. Each method, whether observing distant exoplanets or exploring nearby moons and planets, represents a step forward in humanity's quest to answer one of our deepest questions. Are we alone in this world? Studying the most important thing on Earth has enriched and expanded the search for life on other planets. Extremophiles are organisms that thrive in conditions previously considered uninhabitable. Extremely high or low temperatures, high pressure, high acidity or alkalinity, and high levels of radiation. These amazing adaptations challenge the traditional parameters of life-supporting environments and indicate that life can exist in a much wider range of conditions than previously thought. For example, the discovery of thermophiles, which thrive in the boiling waters of hydrothermal vents deep in the ocean, has led scientists to ponder the possibility of life on celestial bodies with similar environments. Take, for example, the icy moons of Jupiter and Saturn, Europa, and Enceladus, which are thought to have subsurface oceans kept warm by gravitational interaction with their parent planets, creating conditions similar to these deep-sea vents. Similarly, acidophiles and alkalophiles, the search for life in the sulfuric acid clouds of Venus or alkaline hydrothermal vents on Mars, has been inspired by extremophiles that live in highly acidic or basic environments. Moreover, the study of extremophiles, such as radio-resistant microbes that can survive extreme levels of radiation, is expanding potential habitability zones in our solar system and beyond. Mars, with its thin atmosphere and high levels of radiation on the surface, could be home to microbial life underground, where it can be protected from the harshest conditions. Analogues such as the dry valleys of Antarctica, where psychrophiles, cold-loving organisms, thrive, also serve as Earth's model for potential life forms that could exist on the frozen plains of moons such as Europa or Enceladus, or even in the polar regions of Mars. Extremophiles demonstrate the incredible resilience of life and have encouraged scientists to think more broadly and creatively about where life can exist. The discovery that life can thrive in Earth's most extreme environments expands the range of conditions considered suitable for life, and encourages astrobiologists to look for signs of life in places previously thought improbable. This groundbreaking perspective underscores our growing understanding of the universality of life and fuels optimism that we may one day find life beyond Earth. One of the strongest pieces of evidence for the possible existence of extraterrestrial life is the discovery of exoplanets in the habitable zone of their star, or the Goldilocks zone, where conditions may be optimal for liquid water to exist on the planet's surface. Since the launch of the Kepler Space Telescope, scientists have identified thousands of exoplanets, and several of them are in this habitable zone. These planets, such as Kepler 452b and Proxima Centauri b, offer intriguing possibilities due to their Earth-like conditions that could theoretically support life. The discovery of organic molecules in space adds another layer to the evidence. Organic molecules such as amino acids are the building blocks of life, and their presence in meteorites, comets, and the interstellar medium suggests that the ingredients for life may be widespread throughout the galaxy. In particular, the detection of complex organic compounds on Saturn's moon Titan and in plumes of water vapor ejected from the ocean beneath Enceladus's icy crust hint at chemical processes that could potentially support life. Closer to home, Mars provides tantalizing hints of the existence of life in the past and possibly in the present. The Mars rover Curiosity has detected bursts of methane in the Martian atmosphere, which on Earth is mostly produced by biological activity. While methane can also be produced by geological processes, its seasonal fluctuations on Mars lead scientists to speculate that microbial life may be producing it. In addition, ancient riverbeds and lake deposits have been found in sedimentary rocks analyzed by the Mars rovers, suggesting that liquid water, a crucial ingredient for life, once flowed on the surface of Mars for a long time. Another compelling piece of evidence comes from the study of extremophiles on Earth, organisms that can survive in the most inhospitable environments. These include microbes found in the acidic hot springs of Yellowstone, the icy ice of Antarctica, and the crushing depths of the Mariana Trench. The existence of such resilient life forms expands our understanding of the possible diversity of life and indicates that life can potentially survive the extreme conditions found on other planets and moons. Taken together, all of this evidence has generated a great deal of enthusiasm and has prompted continued research in the search for extraterrestrial life. While none of this evidence supports the existence of life beyond Earth, each discovery suggests that life as we know it, or do not yet know it, may well exist somewhere else in the cosmos. The evolution of life in environments very different from Earth's challenges our imagination and scientific understanding, but the principles of biology and evolution allow us to hypothesize how such life forms might have evolved. For example, on a planet with high gravity, evolutionary pressure may produce organisms with strong, robust structures that can withstand increased force. These creatures may have much denser muscles, more powerful limbs, and a compact, squat physique to support their body structure. Increased gravity is also likely to affect the development of a cardiovascular system designed to effectively combat the force pulling blood downward. In environments with high levels of radiation, such as a planet orbiting a star that emits intense ultraviolet or X-ray radiation, life forms can evolve unusual mechanisms for DNA repair and resistance to radiation. For example, microbial equivalents of life could possess highly efficient enzyme systems that rapidly repair damaged genetic material, and multicellular organisms could develop protective layers of pigment or exoskeletons to protect their internal organs. Such adaptations could mirror some extremophiles on Earth, such as the radio-resistant bacterium Deinococcus radiodurans, which can survive incredibly high doses of radiation due to its impressive DNA repair capabilities. In chemical environments very different from Earth's, such as Titan's methane lakes, life may evolve using very different biochemical processes. Instead of water, these organisms may use liquid methane or ethane as a solvent for their biological processes, leading to biochemical processes radically different from our carbon-based life. Their cellular structures may consist of membranes that can withstand extreme cold, and their metabolic processes must be highly efficient to generate energy under such conditions. Scientists hypothesize that the basis for such biochemistry may be silicon rather than carbon, providing a theoretical basis for silicon-based life that could function in these exotic environments. Photosynthesis, a fundamental process for many forms of life on Earth, can also undergo radical changes under different types of stars. On a planet illuminated by a dim red dwarf star, photosynthetic organisms may develop pigments that can absorb the infrared light that is abundant from such stars. Conversely, on planets orbiting hotter stars that emit more ultraviolet light, organisms may develop defense mechanisms and pigments that effectively capture and utilize this more energetic light, protecting themselves from its damaging effects. These hypothetical scenarios demonstrate the incredible adaptability of life governed by the principles of evolution by natural selection. Although the exact forms and functions of extraterrestrial life remain speculative, studying extremophiles on Earth gives us invaluable insights into how life can thrive in environments vastly different from our own. This will expand your understanding of the diversity and adaptation of the universe and help us explore and search for life beyond our world. The discovery of microbial life on Mars will be a major scientific breakthrough with far-reaching consequences, changing our understanding of the universe and our place in it. First, this clearly shows that life is not unique to the universe and suggests that the conditions necessary for life are greater than we think. This greatly increases the chances of finding life elsewhere in space, especially on the many planets found in the habitable zones of their star systems. One of the major scientific implications will be the study of the geology and climate history of Mars. Microbial life has probably adapted to Mars's current conditions, but understanding its origins could reveal vital information about Mars's past environment. If life originated independently on Mars, this suggests that it could arise in a wider range of conditions than those on early Earth. In addition, if Martian microbes share similarities with terrestrial life, it could support the theory of panspermia, which suggests that life can spread to planets via meteorites, comets, or other celestial bodies. This discovery could spur significant advances in astrobiology, especially in developing methods and technologies to detect life in extreme environments. Such findings could spur missions to other celestial bodies in our solar system, such as Europa, Enceladus, and Titan, which are also considered potential habitats for life. It could also accelerate funding and research for more sophisticated space missions designed to study these distant moons and planets with the precision needed to detect microbial communities. Ethically and philosophically, the discovery of Martian microbes will challenge humanity's self-perception. It will lead us to think about the uniqueness of human life and the broader potential for intelligent civilizations in the universe. The discovery could also influence debates about the moral aspects of colonizing Mars or other celestial bodies. Protecting Earth's ecosystems will become a priority, changing the legal and ethical framework for space exploration. From a practical standpoint, this discovery has important implications for planetary defense protocols. Current measures are designed to prevent contamination of Earth and other atmospheric bodies. If life is found on Mars, it will be more important to ensure that terrestrial microbes do not harm the ecosystems of Malaysia, and so on. It could lead to better methods of analyzing spacecraft and better methods of isolating samples returned to Earth. The discovery of microbial life on Mars would be a watershed moment in science, influencing our understanding of biology, stimulating technological and research advances, and prompting deep ethical and philosophical reflection. It would mark a transformative step in humanity's quest to comprehend the full scope and diversity of life in the universe. SETI researchers searching for extraterrestrial intelligence use a range of sophisticated methods and technologies to look for signals from intelligent civilizations beyond Earth. At the heart of their efforts are powerful radio telescopes that scan the sky looking for radio waves that may indicate artificial rather than natural origins. Telescopes are capable of detecting a wide range of frequencies, but SETI scientists often focus on a narrow band around 1,420 MHz, known as the water hole. This frequency is important because it is naturally emitted by neutral hydrogen, the most abundant element in the universe, and may be a logical choice for an intelligent civilization attempting interstellar communication. The search involves not just random listening, but an organized approach to data collection and analysis. Advanced algorithms and software are used to sift through vast amounts of collected data, screening out Earth origin noise and other celestial sources of radio waves. The goal is to identify narrow-band signals that stand out from the random hiss of the cosmic background, as such signals are thought to be produced by technological sources. Projects like SETI at home have even enlisted the help of millions of volunteers around the world who use the computing power of their personal computers to analyze snippets of data, democratizing the search and exponentially increasing the computing power available to researchers. Optical SETI is another promising field, involving the use of optical telescopes to search for short but powerful laser pulses that could be sent by distant civilizations. These pulses, detectable over vast interstellar distances, would be a clear indicator of intelligent technology. Modern photodetectors mounted on telescopes scan the sky, looking for such fleeting bursts of light that are distinct from the continuous glow of stars. Another layer of complexity is added by targeted searches that focus on specific star systems recognized as potentially habitable exoplanets. Thanks to missions such as Kepler and TESS, our understanding of exoplanets has improved, and SETI researchers can now point their instruments at the most promising candidates, increasing the likelihood of finding something noteworthy. In addition, SETI research is not conducted in isolation, but in collaboration with other astronomical observatories around the world. This coordination improves their ability to quickly verify signals that can eliminate terrestrial interference, so that each candidate signal is scrutinized from multiple perspectives. The detection by a known planet of a signal from extraterrestrial life will have far-reaching implications that will change our understanding of man's place in the cosmos. SETI researchers carefully document their findings and engage in peer review processes to verify possible conclusions. Until that fateful day arrives, the work done reflects the human desire to answer one of our deepest questions. Are we alone in this world? The WOW sign, discovered in 1977, is one of the most exciting and sustained in the search for extraterrestrial intelligence. On August 15th of that year, Jerry R. Ammon, an astronomer working at Ohio State University's Big Ear Radio Telescope, observed an unusual radio signal that was 22 times stronger than Earth's background. The sign, which lasted 72 seconds and was so impressive, was recorded by Etchem on a computer monitor with WOW written on the side, giving the sign its now familiar name. One of the mysteries surrounding the WOW symbol is its origin. The signal was found to originate somewhere in the constellation of Sagittarius, near the star group Chi Sagittarius, about 120 light-years away. However, despite many subsequent attempts to detect the signal, Eamon and subsequent astronomers were unable to reproduce or identify it. This scandal led to widespread speculation that the WOW brand was either a foreign proposition or a product of its rarity and uselessness. The characteristics of the symbol can cause violence. Mark WOW. It has a narrow bandwidth, only about 10 kHz, indicating an artificial origin. Cosmic sources typically emit a wide range of frequencies, making such narrow band signals highly unusual and consistent with the kind of focused transmissions we might expect from an intelligent civilization attempting to communicate across vast interstellar distances. Moreover, its frequency, approximately 1420 MHz, coincides with the emission line of neutral hydrogen, a universal marker that scientists believe is ideal for interstellar communication. Several hypotheses have been proposed to explain the WOW signal, ranging from interstellar scintillation to earthly interference. However, none of these have been conclusively proven. The possibility that it could have been a deliberate transmission from an alien civilization continues to excite the imagination, although the lack of repeat detections makes it difficult to form firm conclusions. Some skeptics speculate that the signal could have been an Earth transmission reflected off a piece of space debris, but this remains just a guess with no concrete evidence. Adding to the mystery is the fact that the Big Ear telescope was designed to survey the sky in two orthogonal directions, but the signal was only detected in one channel and not the other. If the signal was of terrestrial or near-Earth origin, it would likely have been detected in both directions. The duration and shape of the signal also do not match known satellite transmissions, further complicating attempts to explain it with conventional sources. The elusiveness of the WOW signal underscores the difficulties inherent in the search for extraterrestrial intelligence. It serves as a reminder of both the vastness of space and the limitations of our detection capabilities. Decades later, the mystery of the WOW signal continues to inspire professional astronomers and amateur sky watchers alike, in the hope that perhaps one day a similar signal could provide more compelling evidence for the existence of intelligent life beyond Earth. In the meantime, WOW. The signal remains one of the most compelling mysteries in the annals of astronomy. The potential existence of life on the moons of Jupiter and Saturn has become a central theme of astrobiological research, primarily because of the unique environments these distant worlds offer. Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, are particularly attractive because of their subsurface oceans, which are kept liquid by tidal heating resulting from gravitational interactions with their parent planets and neighboring moons. A vast ocean is believed to lie beneath the frozen crust of Europa, whose smooth, icy surface is crisscrossed by dark bands and ridges. The proof is in the observations of the Galileo spacecraft, which has detected a magnetic field indicating the presence of a salty conductive liquid beneath the ice. This subsurface ocean may be in contact with the rocky mantle, potentially allowing the chemical interactions necessary to support microbial life. If hydrothermal vents like those found in Earth's oceans exist on Europa's seafloor, they could provide the energy and nutrients necessary for life. On Earth, these deep-sea vents are home to teeming ecosystems teeming with life, independent of sunlight and relying on chemosynthesis to convert chemicals into energy. Enceladus, though smaller in size, presents an equally interesting case. The Cassini spacecraft made remarkable discoveries during flybys, capturing geysers erupting from the Moon's south polar region. These plumes are composed of water vapor, molecular hydrogen, and organic compounds, suggesting the presence of a subsurface ocean beneath the ice shell. The presence of molecular hydrogen found during the Cassini survey indicates hydrothermal activity on the ocean floor, where the interaction of water and rocks produces hydrogen. Such environments may provide a source of chemical energy for life, similar to ecosystems found near Earth's hydrothermal vents. Titan, another moon of Saturn, offers a different but intriguing environment for potential life. Unlike Europa and Enceladus, Titan has a dense nitrogen-rich atmosphere and liquid hydrocarbon lakes on its surface, consisting mostly of methane and ethane. While this is very different from the water-based life we know, it is conceivable that life could have evolved using these hydrocarbons as solvents. Scientists speculate that Titan's exotic chemistry may contribute to the formation of complex organic molecules, and possibly prebiotic chemistry that could serve as a precursor to life. Ganymede and Callisto, two of Jupiter's other major moons, also have features that indicate the presence of subsurface oceans. Although it is less studied, the possibility of liquid water beneath thick layers of ice adds it to the list of intriguing candidates. The idea that life can survive in these alien environments is supported by the discovery on Earth of extremophiles, organisms that thrive in extreme environments, from boiling acid springs to deep underground rock formations, demonstrating the amazing adaptability of life. Exploring these moons to confirm the existence of life involves several technological challenges and future missions. Instruments designed to analyze the composition of surface ice, study plumes, and potentially drill through layers of ice to reach the deep oceans are in various stages of development. NASA's upcoming Europa Clipper mission is designed to conduct a detailed exploration of Europa's icy envelope and subsurface ocean, while the European Space Agency's JUICE mission will study Jupiter's icy moons, including Ganymede. Overall, the moons of Jupiter and Saturn represent some of the most promising places in our solar system to search for extraterrestrial life. The presence of subsurface oceans, organic molecules, and energy sources on these distant worlds creates compelling conditions in which living organisms can exist. The discovery of such life will revolutionize our understanding of the biology, biochemistry, and potential prevalence of life in the universe, with profound implications for our place in space. Confirming the existence of extraterrestrial life is a formidable scientific challenge with many technological, methodological, and philosophical problems. One of the main challenges is the vast distances and scale of space. Even in our solar system, places like Mars, Europa, and Enceladus require a significant investment of time and resources. Interstellar distances exacerbate this problem. The nearest star system, Alpha Centauri, is more than 4 light-years away, making it impossible to directly explore with current technology. Another major obstacle is the search for and identification of indirect markers of life, or biological signatures. They take many forms: chemical compounds, various atmospheric compounds, and even complex organic molecules. For example, the presence of methane bursts on Mars, detected by the Curiosity rover, remains intriguing but inconclusive because such methane may be produced by geologic rather than biological processes. Similarly, observing oxygen, methane, or water vapor in the atmospheres of exoplanets with telescopes like the forthcoming James Webb Space Telescope may hint at life, but distinguishing biological sources from abiotic sources is very difficult. The environment itself presents serious obstacles. Harsh conditions such as extreme radiation, low temperatures, or high pressure require specialized equipment to explore and collect samples. Mars rovers and landers designed to explore such environments must be robust and capable of performing complex analyses remotely with minimal error. Technological limitations also extend to our current inability to drill deep through ice shelves to access subsurface oceans on moons such as Europa and Enceladus, where life could potentially exist. Pollution control is another critical issue. Ensuring that potential life found on other planets or moons is truly extraterrestrial and not a stowaway from Earth requires careful sterilization of spacecraft and instruments. Conversely, returning extraterrestrial samples to Earth must be done with extreme care to avoid contaminating our biosphere with potentially unknown and dangerous microorganisms. Scientific consensus and reproducibility further complicate the confirmation process. Any claims of the discovery of extraterrestrial life should be subject to scrutiny, peer review, and independent verification. The implications of such a discovery are so great that the scientific community has exceptionally high demands for evidence. This means that even if a potential biosignature is detected, it must be observed consistently and confirmed by multiple lines of evidence and by different teams of researchers. The detection of intelligent extraterrestrial life presents a number of challenges. Projects such as SETI involve listening for radio signals from intelligent civilizations, but deciphering these signals, distinguishing them from anthropogenic interference, and confirming their extraterrestrial origin is a complex and difficult task. The famous WOW, discovered in 1977, this is a good example of an exciting but unreproducible discovery that led to debate and further research without definitive conclusions. Finally, there are philosophical and definitional problems. What is life? Traditional definitions based on terrestrial biology may not be applicable to organisms with different biochemical compositions. The concept of life we don't yet know is forcing scientists to expand their criteria and methods to ignore other life forms because they don't fit past assumptions. Confirming extraterrestrial life requires traveling vast distances, developing advanced technologies, managing the risks of contamination, ensuring reproducibility and reliability of scientific data, deciphering potential intelligent signals, and expanding our ideas of what life might be like. These challenges are daunting, but also stimulate innovative solutions and interdisciplinary collaboration, pushing the boundaries of science and our understanding of the universe. The discovery of extraterrestrial life will revolutionize our understanding of life on Earth, affecting fields as diverse as biology, philosophy, astronomy, and even theology. From a biology perspective, the detection of extraterrestrial life would provide invaluable insights into the diversity and adaptability of life. This would expand our understanding of biochemistry beyond the Earth concept and provide a comparative basis for studying the principles of life. For example, if extraterrestrial life is discovered to use a biochemistry different from carbon-based life, perhaps silicon-based or based on a completely unpredictable molecule, this would force a rethinking of the fundamental assumptions for life and could reveal new biochemical processes previously thought impossible. This discovery will breathe new life into evolutionary biology, opening a new context for studying the evolution of life in different environmental conditions. On Earth, evolution is influenced by various factors such as climate, geography, and the presence of chemicals. The discovery of life that evolved in other environments, such as the high radiation environments of an exoplanet orbiting a red dwarf star or the cool methane lakes of Titan, it would suggest new pathways and mechanisms of evolution, expanding the scope of evolutionary theory. From a philosophical point of view, confirmation of the existence of extraterrestrial life would challenge long-held views about humanity's place in the universe. The Copernican principle, which asserts that the Earth is not the center of the universe, will take on even greater significance if we assume that life is ubiquitous rather than an earthbound anomaly. This paradigm shift may affect philosophical discussions about the uniqueness of human life, our ethical responsibility to other life forms, and our role in a larger, perhaps teeming, cosmic ecosystem. Theologically, the discovery could lead to a rethinking of religious doctrines and texts, especially those dealing with the uniqueness of human life and the concept of creation. Different religions may integrate these new findings into their worldviews in different ways. It could potentially lead to a richer and more nuanced understanding of the spirituality that encompasses a universe filled with life. In terms of scientific methodology, the discovery of extraterrestrial life will emphasize the power and importance of interdisciplinary research that integrates astronomy, chemistry, biology, ecology, and other fields. This will require the development of new scientific tools and methods to detect, analyze, and understand life forms with potentially unfamiliar anatomy and biochemistry. This technological and methodological innovation may have spin-off benefits for other scientific fields and disciplines. From a societal and cultural perspective, discovery can foster a new sense of unity and purpose. Humanity may come to realize itself as part of a larger cosmic family, prompting global cooperation in scientific, ecological, and research endeavors. It could also awaken scientific curiosity and inspiration, similar to the excitement and wonder of the Apollo moon landing, but on an even larger scale. Economically, such a discovery could stimulate investment in space exploration, biotechnology, and related industries, leading to technological advances and new market opportunities. The desire to explore, understand, and perhaps even connect with extraterrestrial life could be a major driver of innovation and economic growth. The discovery of extraterrestrial life will have a transformative impact on our understanding of life on Earth, changing scientific paradigms, philosophical views, theological beliefs, and societal values. This will confirm that life is a fundamental cosmic phenomenon, prompting humanity to rethink its place in the universe and its relationship with other life forms, potentially leading to a more cohesive and enlightened global community.